All right, so divergent series, the absolute value of your common ratio is greater than 1. And if it's convergent, then the absolute value of your common ratio is less than 1. And we looked at a couple of geometric series here, and we found that the common ratio for number 27 was 1/4, and that's convergent. So it has an infinite sum. And the formula for infinite sum is right here. And we found out that that one added up eventually to -4/3 for the total for that sum from -1 all the way to positive infinity terms out of that. And then number 28, we saw that the common ratio was -2. The absolute value of that is 2. 2 is greater than 1, so that's a divergent series. So the divergent series, what you notice is that the terms start spreading out further. Convergent, they start getting smaller and smaller, getting closer to 0. That's what happens there as you're doing that. So if you look at the ones below that, you could do the same things. You could find your common ratios and decide if it's convergent or divergent. That's the big thing, and then be able to find that sum. When you get to those that have the summation symbol, this is not a calculator activity like the others were, but it's going from 1 to infinity here. It doesn't have a finite number of terms, so you can't use the calculator to do that. What you notice here, these are geometric series. That number that's got the exponent, that's your common ratio. Those are all common ratios. So all you got to do is look at that to decide, is that convergent or divergent? So look at the number that has the exponent, 1/3, so that's a convergent series. So you could find the first term, that's the only one you need, and then use that to find the infinite sum. So the first term, you plug in a 1 for k, and you'd have 5 times 1/3 to the 0 power, which is 5. So to find the infinite sum, it'd be 5 over 1 minus 1/3, which is 5 over 2/3, which is 15 over 2, would be the infinite sum of that. You look at number 32, the R is 5, which is greater than 1 already. So that is definitely a divergent series, so it doesn't have an infinite sum. Okay, so a little bit different, but it's the same kind of look as some of those others we did yesterday. Let's go down there to the bottom of that page and look at those permutations and combinations. All right, so when we're dealing with permutations, order matters. Combinations order doesn't matter. Okay, so permutations is like arranging things in a certain order. So like if I wanted to find out how many ways there are to arrange these 3 people in this row in 3 seats, that's a permutation, because whoever's in the front seat's in the first spot, and you got a second spot and a third spot. That's a permutation, order, arrangement. Those words, when you see those, you think permutation. Combinations is like if I took everybody in this class and wanted to figure out how many ways are there to pick groups of 4, or pick 4 people at a time. So it'd be 20, there's 28 of us today, 28, and then we choose 4. Combinations, there's no rank. If we were running a foot race, it would be a permutation if we want to do the first 4 places, because there's a rank and an order to it. So permutations, the way you know to use permutations is it has some sort of order, arrangement, ranking, that sort of idea, okay? Permutations, we're going to use NPR, and the N is how many things you have to choose from. So like if we're picking people in the class, there's 28 people in here. That's how many people we have to choose from. R is how many things you're choosing at a time and arranging. So with that example with the 3 people in the row, I've got 3, I'm choosing 3. So it's a permutation with 3 and 3. The formula, which you don't have to memorize, is n factorial over n minus r factorial. The combination formula with n and r. N, again, is the number of things you're choosing from. R is how many you're choosing at a time. Okay? So it's n minus r factorial, the same thing, and then r factorial. You do not have to memorize that formula. They're not going to ask you to do this on the non-calculator portion. This is going to be a calculator activity. I'm going to show you how to do it with the graphing calculator. So get those out, and we'll talk about how to do this. Okay? Permutations, order matters. With permutations, there's going to be more, it should be bigger numbers than combinations. Because combinations, when I pick 4 of you, it doesn't matter what order I pick you in. It's the same 4 people, right? So if I pick Bethany, Ryland, Carter, and Jagger, if I pick you guys as a group, it doesn't matter what order I pick you in if I'm just picking a group. But if I rank you in first, second, third, and fourth place, then that's a permutation. And once I pick whoever's in first place, if I just swap one of you, it's another different permutation. Okay, so permutations is going to be larger numbers than combinations are. All right, so let's look at how to find this on the calculator. So on the graphing calculator, my screen a little bigger here. Hit the math button, which is right underneath the green alpha button. And then you're looking for PRB. If you've got one of the color ones, it's going to say PROB. So PRB, I think, is what most of you've got the black and white one to look for. And you should see a menu come up like this. So just press the right arrow key till you get to PRB. And I'm looking for NPR and NCR. Those permutation, combination. Okay. When you hit that, depending on how your calculator is set up, you may get the little boxes, or it may say answer and then NPR. If it says answer and NPR, I'm going to show you how to do that. If it has the boxes, it's pretty obvious how to do that. Okay, so that's where those are. Math over the probability is what that stands for. Okay, so let's look at number 35 and see if we can figure out what we're going to do here. So 15 AFC teams in the NFL. How many ways can 2 play against each other in the AFC championship game? So this is before the season starts. We want to know how many different ways could the championship game in the AFC turn out. What 2 teams could be there? So is this a combination or a permutation? Combination, because it's not ranking them at all yet, right? It's just how many different ways could that game happen? So this is going to be a permutation. So it's going to be 15 permutation. How many teams play in a game? 2, right? So we're going to do 15 permutation 2 because we're picking 2 teams. So if you've got the calculator and it does it doesn't have the boxes, you're going to want to type the 15 first. So type 15, hit math, go over to probability, get your permutation, and then you'll type 2 after that. So 15, get the NPR button, and then type the 2. You've got the boxes there, you just put them in there in that way. Okay, and then when you hit enter, you should get 210 different ways for that game to happen with 15 teams. 15, 210 possible ways for that to happen. Number 36, we did permutation. We're supposed to do combination. What was I thinking? Sorry about that, guys. My brain was thinking about number 36 already. Combination. Back up. 15, math, combination. 2. That should be much smaller. 105 ways. Half as many ways. Yeah. Yeah, you need top 15. Where are they? Anybody else having calculator not doing what it should be doing, or what mine's doing? You need to type in the 15 first. So clear it, hit clear, type 15, and then math, or probability, GR. Okay. Anybody else? All right. So combination on that one. Apologize for screwing that up. That was awesome. Way to go. And then 36, got 35 violin players. There's a first and second chair. So that's a ranking, right? So that's a permutation. So we're going to do 35 permutation, 2 chairs. 35, go to math, probability, permutation, to 1,190 different ways for 35 people trying out to make that first or second chair. Now, we tend to oversimplify things a little bit, but think about, just to kind of give us another example of this. It's not on your paper. How many guys are on the football team? Anybody know? A rough estimate, just close. 50? Okay, so there's 50 guys on the football team. Right now it's workout season, right? So you get in smaller groups, right, to do your workouts. Well, let's say they weren't grouping you up in skills players and other things. Maybe you're all doing like a CrossFit thing where it really doesn't matter if you're a skills player or a lineman, and you just want to make groups. You think about how many different ways are there to form groups of 4. So 50 players in groups of 4. A few more than that. So that would be, is this a permutation or a combination? Combination, because we're just wanting a group to travel through the stations together. So we're not ranking anybody as a leader and the different things, that sort of idea. So we're doing 50 combination 4. How many different groups are there? So 50 math, probability, combination 4. 230,300 different ways to make y'all into groups of 4. Big 4 people. That's a lot of ways. I'm not 100% certain that Coach Hopper goes through that process, but the idea is, if you think about does anybody ever play cards in here? It's getting to be a dying thing. Not many people play cards, but if you play cards or play poker, I've got a friend that plays poker and he does the you see poker on ESPN. He plays those sort of things. He's that good. He wins some money doing that. He loses a lot too. He wins a good bit doing that. But why does one hand beat another? Well, when you talk about poker and maybe it's 5 card, and how many different hands are there drawing 5 cards out of a 52 card deck? So 52 cards and then combination with 5 at a time. Let's look at that. 52 combination 5. How many 5 card hands are there? So 52 math combination 5. 2,598,960 different hands. Yeah, it's a lot of different possible hands that you could get in from one deck of cards. Now, best hand that you can get would be a royal straight flush. That's the best hand. It wins every time because it's the cards Jack, Queen, King, Ace in the same suit, so, of hearts, of diamonds, and clubs, that sort of thing. That's the best hand. It wins no matter what anybody else has. What's the probability of getting that hand? 1 out of that number. That's why it's the best hand. That's the only way to get that hand. That's it, assuming you don't do any like wild cards or something like that. So, and a lot of times they don't on the competitive poker. They don't do wild cards a lot of times. Okay, so the reason one hand beats another is because its probability is lower of getting that hand. So that's why the royal straight flush beats, you know, just a straight. A straight would be a successive number of cards from one suit, and then a flush would be the what is a flush? Flush is same suit, but the higher ranking cards, and then but probability has something to do with it. So combinations come into that with the card hands. That's why they one card hand beats another. Let's look at 37 real quick. Get back to some problems here. United States can have 10 gymnasts on their next Olympic team. How many different teams of 10 gymnasts can be selected from 18 people trying out? Is this a combination or a permutation? Combination, because we're not saying, okay, you're the best, you're the second best, and all that stuff. We're just making up a team of 10 people out of 18. I'm going to say probably you pick 10 out of that 18. They're all better at gymnastics than any of us that are trying out, because it's going to be a good team no matter which 10 you pick. So how many different ways? 18, math, combination, 10. 43,758 ways to pick a team of 10. Now, number 38 says we're going to arrange 8 reference books on a shelf. That's a permutation. So how many are we choosing, though? We're going to arrange 8 books on a shelf. There are 8 things to choose from. If we're going to arrange 8 books, there's 8. So we're going to do 8, permutation 8. 40,320 ways. So think about it this way. You number the books 1 through 8. The first way you put them up there is 1 to 8. When I swap number 1 and number 2, that's the second way. Then the next way, if I put number 1 back in the first position and swap 2 and 3, that's another way. Swap 3 and 4. You know, do that the whole way through. So it adds up really, really fast as to how many different ways arrangement can be. Because all I've got to do is just change 2 of them's position, and it's a different permutation. If it's just combinations, not a one.
I remember in elementary school we did this. I had trouble with it because I didn't know what the permutations. So I get really hard numbers. I make like 4. They're simple.
Yeah, it wouldn't be. I don't think it'd be this large with that. Let's think about kind of this thing called the fundamental counting principle. This is not on your paper, and you don't, just pay attention here. And it makes sense once you see it. You guys are getting close to. Some of you may be driving already. Some of you are getting close to driving. A lot of folks like to have personalized license plates. And in the state of Tennessee, how many characters can you have on a license plate? 7. Okay. So 7 characters. How many choices are there for each character? 26 letters. You can have numbers too. So there's 0 through 9. That's 10 numbers. So there's 36 possibilities for each blank. And I don't know if you would want to, but you could have the same letter or number in every blank if you wanted to. Now you have to submit what you want your personalized plate to be, and they have to approve it. But sometimes things get submitted that aren't approved because they're not what we want to represent Tennessee with. But to find out how many different possible personalized plates there are, you multiply all those together. So that's 36 to the 7th power, right? 36 to the 7th power. That's a big number. That's scientific notation right there. That E10, that means 7.83641,641 times 10 to the 10th power. So you move the decimal place 10 times to the right. That's a stinking bunch of different plates that could be.
Just truthful.
Yeah.
Ants Malone chicken.
Okay.
Thank you.
So let's think about PIN numbers on your phone, like the passcodes. How many digits are your passcodes on? 6 digits? So 6 digits. Let's say you can't repeat a digit. How many choices are for the first digit? So you can do letters on passcodes too? Passcodes. No, passcodes. So how many choices, on a passcode, how many digits are there? There's 10 numbers, right? And then if you can't repeat, how many are choices for the second one? The third one? Fourth? And then you multiply all those together, and that's going to give you how many possible passcodes you could make. Some of y'all are typing that in. Can y'all tell me that number? Because I can't do that in my head. I'm not that bad. Say it again. That's how many possible passcodes, 6-digit passcodes there are. If you did 4-digit passcodes, then you take off the 6 and the 5. So divide that by 30, and you get 4-digit passcodes. If you can't repeat a digit. If you can repeat a digit, then the number goes way up. Because you get 10, 10, 10, 10 out of that. That's the... Yeah, I'm just saying if you couldn't. If sometimes you can't. Like some websites, like if you're putting in a password for a store website, a lot of times you have to have certain things in there, a capital letter, a special character, those sort of things. You've got to have those things. So that increases the number of characters possible, which makes your password even harder to guess. That's the idea. That's the reason behind all that internet security. A lot of the permutation combination stuff goes into cryptology, which is you can talk about encryption. We've already talked about encrypting your data on your cell phone or encrypting your data on your computer. When you encrypt your data, it uses math to hide all the data that's on there. And there's a ransomware virus that goes around, and it will encrypt your data until you pay them to unencrypt it. And it's a math formula that they've used to lock all your stuff up. And without their formula, you can't unlock it. And so there's a whole area of math that you could go into that takes this idea and blows it up. Huge. Exactly. Yeah. But you got to be really, really smart. Wow. All right. Let's look at the weird looking curve there. This is the normal curve. It's called a bell curve. You may have heard that before. But the normal distribution is what that is. And the way the normal distribution works, no matter what the data is, if it's normally distributed, then it always has certain characteristics. The mean is always in the middle. This curve represents how much of the data fits in that area. So the mean goes in the middle. This is your average. The majority of your data is going to be closest to the average. It kind of makes some sense, doesn't it? As you get more and more samples, the more it becomes closer to normal. And with that, let's get some percentages in there. If the mean is in the middle, then these two sections right here are going to hold 34.1% of the data points, each one holding 34.1%. Okay. These sections are created by what's called the standard deviation. The standard deviation is a measure of distance from the mean to the data points. It's kind of like, it's not quite just an average of the distance between a data point and the mean. It's a little bit more complicated than that, but that's kind of what the idea of it is. The standard deviation is how far the data spreads out from the average, is what each line represents going out from the center. So within one standard deviation to the right, there's 34.1% of the data points. So if we had 100 data points, 34 of them are going to be at the mean or one standard deviation above it. 34.1% are going to be at the mean or one standard deviation below it out of that. So that's 68.2% of your data is within one standard deviation of the average. If it's normally distributed, that's what's happening. And once you get into the law of large numbers, the normal distribution it shows up everywhere, all over the place. Okay. Now, the next standard deviation away is 13.6% on each side. All the time. If it's normally distributed, it's always these same percentages. Okay. The next standard deviation away, that block right there, is 2.2%. Same thing over here. It's always these same numbers. And then the very last little small bit there is 0.1%. I had a professor in college that taught psychology, and he did our test on the normal distribution curve. Whatever the average was for the class, no matter how well the class did or how bad the class did, these two red blocks in the middle were C's. So if you were within one standard deviation above or below that average, didn't matter if everybody did well and the class average was 95. 95 became a C. And you would fall in here. And then if you were within bigger than one standard deviation away, but smaller than two standard deviations away, then you fell in this place. And this area became, these two blocks became B's. These two blocks down here became D's. To get an A, you had to be in this little kind of spot. 0.1% of everybody that took that test got an A. In a class of 50 people, guess how many people that is? One. One person gets an A. But also, one person gets an F.
Is that how we grade everything?
Everything. Every single thing. Yeah. But it made the class very competitive. I was the only non-nursing major in there. So I may have caused someone to not be a nurse. I was going to be in the purple box. I didn't care what I got in the purple box. So there may be somebody that did not quite make the grade to get into nursing school because I took a psychology class once. And the guy graded it like that. Had he graded it regularly, just like normal stuff, it would have probably ended up about the same because it was always normally distributed. There was 50 of us in the class. It was a really big class. So that's the data tends to fall this way anyway. All right, so let's apply this curve and these percentages to some of these problems. Okay, so the first thing we want to read here is it says the heights of 28 people in the class are normally distributed with a mean of 65 inches and a standard deviation of 1.5 inches. Okay, so if we apply that to this curve, where does the 65 go? right there in the middle. 65 is that point right there. Right there in the middle line. What does this line represent? What number? 1 standard deviation away. So that would be 65 plus 1.5, which would be 66.5. The next line up, add 1.5 to that. So that'd be 68. Add 1.5 to that. 69.5. To go the other direction, instead of adding 1.5, what are we going to do? Subtract it each way. So 63.5, 62, 60.5. So because this data is normally distributed, then we know that 0.1% of the 28 people are taller than 69.5 inches. We know that there are 68.2% of the people that have a height between 63.5 inches and 66.5 inches. Let's look at these questions. It says, what percent of the students are within 1 standard deviation of the mean? That is this area right here. That area is 1 standard deviation away from the mean. 1 standard deviation to the right, 1 to the left. That total area is 68.2% because it's normally distributed. Number 40 says, what percent of the students are between 65 and 69.5 inches tall? 65 is here, 69.5 is here. Between that would be all of this. So what do we do with each of those percentages? Add them up. .9%, almost half. That would make sense if it's normally distributed. You know, it splits it in half, doesn't it? This is 50%, this is 50%. 41 says, what's the probability that a student is at least 62 inches tall? What's at least mean? Or more, right? So probability is going to be the percentage from 62 up. So we're going to add 13.6, 34.1, 34.1, 13.6, 2.2, and 0.1. Or we could take 1 minus 2.2 plus 0.1. And we're going to get the same number. That'd be 97.7%. Whether you add this direction or subtract from 1 in those directions. All right, let's talk about a little bit more statistics level kind of stuff. This is what's called a z-score. A z-score is when you take data sets and you convert them to what's called a normalized set. When you normalize data, the reason for doing that would be like if I measured everybody's height in this class and then went back to first block and measured everybody in there, would the averages be the same? No, they're probably not going to be exactly the same. They're going to be off by just a little bit probably. So when I look at 2 different data sets that have a different average, it's hard to compare them directly. But if I normalize the data and do z-scores, then it makes it easy to compare the 2 data sets. Okay? So z-scores are used to help us be able to compare different sets of data. So to calculate a z-score, this is your formula. And I'll explain what each of these things are. That's your data point minus the mean over the standard deviation. That's what that stands for. X is the data point. X bar is the mean. This little looks like a cursive O, but it's the Greek letter sigma is what that really is. But that's the standard deviation. Okay, so all that information is going to have to be given to you if you got to find a z-score. So they give us the mean of 81, a standard deviation of 6. Brittany scored a 68. Find her z-score. We want to compare Brittany's score to somebody else's in another class, but we want to compare it normal with a normal curve out of that. So we're going to plug all that stuff into this formula. 68 minus 81 divided by 6. That's how we're going to do that. $68 minus 81 divided by 6. We'll round to 2 decimal places. So that'd be a negative 2.17. Is that to the left or to the right of the mean? Left, because it's negative, right? Z-score is going to be negative if the score is less than the mean. Now, what you can do with that is you can compare those, how far was she away from the mean. When you talk about z-scores, you're trying to compare different data sets that have different means. When you talk about ACT, it's a normalized test. When you take it on Saturdays, they compare your scores to everybody else that took it the exact same day. So it's norm referenced is what it's called. And they compare what the average is, and it still takes 59 or 60 questions to get a 36 on the math part. Still got to get 59 or 60 right, because there's going to be somebody that took it all across the nation that did get all 60 of them right. So depending on who else takes it the day you take it, that can change your score by 1 or 2 points, because it's norm referenced. And it deals with the normal distribution. It talks about comparing z-scores and stuff like that. So really, you can we get into a lot of this. If you take statistics, we do a lot more with this, and you kind of get a better understanding of it. I'm trying to blast through it here with you guys, but if you take statistics, we do a lot deeper understanding of this stuff and why you use it and when you can use it and how you can use it. Let's look at 43, and then we'll get into some calculator stuff. 43, the price of a gallon of milk at various grocery stores is normally distributed with a mean of $2.95. Quick Mart sells milk for $3.44 and has a z-score of 1.4. They want us to find the standard deviation. This is an algebra problem. We know the z-score. We know the data point. We are missing the standard deviation. This is 0.49 over sigma. Those two dudes multiply. Divided by 1.4. Standard deviation would be 0. Let's go 2 decimal places there. 0.49 divided by 1.4. Right. It is 2 decimal places. 0.35. Nice even number. Standard deviation is 0.35 for that situation. In statistics, you're not going to do anything with it in Algebra 2, but in the statistics class, you might need to know the standard deviation in order to apply another thing for testing some data with it. So this is kind of the reason for being able to do that sort of thing. So like I said, we go a lot deeper with this in statistics than we're ever going to get in Algebra 2. Let's look at the next thing. This is a calculator stuff. So make sure you got your graphing calculator handy. I'm going to show you how to do these with that. So the average credit card debt for a group of 50 college seniors is normally distributed with a mean of $3,000 and a standard deviation of $800. What percent of the students have a
History is full.
Yes.
Connor Harwell checking in.
Okay.
Thank you.
What percent of the students have credit debt between $2,800 and $4,000? Okay. Now, if you make the normal curve and draw it out and put the numbers there, 2,800 and 4,000 are not on those nice marks. So this is where we've got to use the calculator to do this. So I'm going to show you how to do that. What you're going to look for is you're going to hit second and then the vars button. And then you're looking for normal CDF. It's not a grade or anything, but it's just a review of everything you might look at. So normal CDF is what we're looking for. So go to calculator, hit second. Bars is right beside the clear button, right here. And you should get to this menu. Second, and then it's variables is what it really is supposed to. I just say bars because it's fun. But second, and it gets you to the distributions. And then we're dealing with a normal distribution, so that's why we're doing normal CDF. What the CDF does is it adds up area between certain spots. So number 2 is what we're looking for. And the lower that we're looking for is the lowest number is 2,800. So I'm going to put 2,800 there. The upper is, the high number is 4,000. That weird looking symbol there is the Greek letter mu. It's the mean for the data, 3,000. And then sigma, we've already talked about, that's standard deviation. So those go there. And then we're going to hit enter. And what this is going to do is it's going to find the total area between those 2 points. Same way we were doing on the problem before, but it's using different spots that are not on the nice standard deviation. So it's 49.31% is the percentage of students that have credit card debt between $2,800 and $4,000. Okay. Number 45 says find the probability of that a student will have a credit debt of at least $2,100. What's at least mean again? Minimum of $2,100, so it could be more. All right. So when we go to our normal CDF, we're going to do that again. Our lower is 2,100, but our upper is who knows how much. We don't know what kind of debt they could have accrued. So we need something that represents infinity. Guys, take your earbuds out. Because I know you got something playing in your ear, and that's disrespectful. I don't care where you're from. All right. Our upper is going to be something that represents infinity. To represent infinity, we're going to put 1, then hit second, and this button right above the 7, the comma button. And what that is notation for scientific notation, and we're going to put a 99 after that. That's 1 with 99 zeros after it. That's going to be close enough to infinity for us. Okay? It's a big, big number. Okay? And then our mean and our standard deviation are the same, so we're not changing those. And we hit enter, and it gives us the percentage that, or probability percentage, they're the same thing, that someone would have at least a $2,100 debt. 86.97%. I hope that's not the case for you guys when you go to college. Bad news. Approximately how many students have a maximum credit debt of $3,500? So what's maximum mean? The most. So it could be anything less than that. So what's the least amount of debt we could get out of college with? $0, right? So when we go to our normal CDF again, our lower is going to be $0, and our upper is that maximum $3,500. Everything else is the same. Paste and enter. 73.39% of how many students? Of 50. So how do we find out how many students that is? You multiply that times how many students that we studied, 50 of them. 30, we can't have 0.6 of a student, so we'll just round down to 36 students. $47, approximately how many students have credit debt between $3,000 and $4,800? So this is a lot like number 44, except for we're going to find that percentage and then multiply it times 50. That's the only difference. So I'm going to go to second, bars, normal CDF. My lower is 3,000. My upper is 4,800. Everything else is the same. 48.78% times 50 students in our study. So that'd be 24 students. Have debt between those two numbers. That's a lot. Think about it. Graduating from college, you have nothing, and you're looking for your first job, and you're already in the hole between $3,000 and $4,800. That's a lot. All right, so I know that isn't the best of